All right, we're going to go ahead and get started. Hopefully Miss Richards and Miss Taylor's class have joined us. If you have joined us, please come and meet up with us on today'smeet.com/PerlaScience136. That'll allow us to talk with each other, and it'll make sure that we are aware that you are out there somewhere in the universe and you're chatting with us. Okay, so last week we were looking at magnets, and primarily how magnets interact with what? You remember?
Iron.
No?
Steel.
No? Ramson, we were looking at how magnets interact with what?
Other magnets.
With other magnets. We were taking magnets and putting them together, and we realized that magnets interact with each other in a really interesting way. What are some things that magnets do when they interact with each other? You remember?
They repel.
They repel. They push each other apart. Okay, what else?
They attract.
They attract. They pull each other together. And it seems like a really odd thing because you say, why do magnets sometimes repel and sometimes attract? And we discovered that there's something very special about magnets. And there's, what is it that they have? We said we call them poles. We said magnets have two sides. And in fact, we said magnets have two sides known as poles. And these poles interact with each other. It's these poles that create the magnetism. Okay, we said if you have a north pole and a north pole and you bring them together, okay, the magnets push each other apart. They want nothing to do with each other. However, if you bring a north pole and a south pole, you will find that magnets interact with each other by attracting. Okay, and so magnets have two poles. And an interesting question that we posed last week was, what would happen if I cut this magnet in half, like right here? Or if I cut it right there, would I have a magnet with two north poles? No. So what did we say would happen, Jackson?
That the very end of the place that you cut off would just become a south pole.
Okay, right. So if I cut off the north pole on this magnet, if I were to cut it right here, right where my finger is, that would become the new north pole. So a magnet always has to have a north pole and a south pole. So that was something really interesting that we discovered about magnets, the way they interact with each other. And we also found that the Earth is a magnet. How did we prove the Earth must be a magnet? Serenity, do you remember that?
We tied a string to a magnet and you spin it, and then whatever way it was facing, like north was facing north and south was facing south.
Okay, so we found that when we hung a magnet from a string, the magnet always pointed in the same direction, which meant that there was something forcing this magnet to move a certain way. And we've learned the only thing that can make a magnet move a certain way is what?
A magnet.
Another magnet. And so we said, well, there's no other magnets around, therefore the Earth must be a magnet that has a magnetic field that is causing this to act that way. Okay. Now I don't have a picture of the Earth's magnetic field because can you see the magnetic field on this magnet?
No.
You can't. Okay? But the magnetic field goes from what? We know that the magnetic field tends to pull, and it always pulls between which sides?
North and south.
North and south. And so when you start to say, well, what would this field look like if I could see it? What would it look like? Okay? Well, it's pretty interesting because if you had this magnet, you would have magnetic lines that go like this. Okay. And these magnetic lines would go from where to where?
North to south.
From north to south. Okay? Which means that a piece of iron, if I were to put a piece of iron in here, okay, it would get sucked towards the ends. Right? Okay, now, what if I had, Callie, can you get me a paper towel? What if I had a different kind of magnet? What if I had a different kind of magnet? What would it look like? A wet paper towel. If I had a wet paper towel, if I had a flat magnet, like the ones that we work with, one that looks like this, the question is, what would the field lines on that one look like? Well, they would have to look the same way. The field lines would have to go from what to what? That's fine, Callie. They would have to go from north to south. Okay, and so anytime you take a magnet and you draw field lines, your field lines always have to follow which pattern?
North and south.
They always have to go north to south. Okay, so you'd always have to have a north-south pattern. So if I were to take this magnet and put it like this, okay, well, I know that one side of the magnet is what? North. The other side of the magnet, now we called it A, but it's not really called A, is it?
No.
What is it called? North. And so let's say, and we don't know right now, but let's say this is, and we could find out easily. So if this is the north, and it's attracted to that side, what's this side?
South. South.
This side is the south. This side must be the
North.
north. And the way I can prove that is if I bring the north to this side, see, now I flipped it. If I bring the north to this side, I can feel it repelling. It doesn't want to be there. So this is correct. Now, if I was going to draw these field lines, they would have to go from how? Okay, those field lines would look something like this. Whoa. Okay, those field lines would look something like this. Stop spinning. Okay. So the field lines for that magnet would look something like this. And so what does that mean what do those field lines represent? What that means is that if I took a piece of iron and I put it here, and this magnet was strong enough, it would follow these field lines and boom, it would stick to this side. If it was here, it would follow these field lines and stick here, boom. Okay? If I had something here, so the things tend to want to stick to the north or the south. That's what the field lines would look like. What do you think the field lines for the Earth would look like? So if I were to draw the Earth, what would you guess the field lines would look like for the Earth? Okay? So if we were to say, all right, here's the Earth, right? And you've got all your countries. You got little Florida here, South America. Okay, Alaska's up here somewhere. Okay, and then here you got Europe, Africa. Okay, so there's our Earth. Okay, what would the field lines look like? Where's the North Pole?
On the top of the world, the bottom of the world.
The North Pole of the magnet is on the bottom of the world, right? This is the North Pole of the magnet. This is the South Pole of the magnet. How do I know this? Because when I put a magnet, it points this way, right? The north part of the magnet points up, which means what part of the Earth must that be?
South.
That means to be the south because the north is attracted to the south. Does that make sense? Okay. Now, so what would the field lines look like? What do you think? Yeah, the field lines of the Earth are something like this.
Like a year.
Okay.
It looks like an apple.
And they all go into, even though my picture's not very good, they all go into north. Right? So when you look at these magnetic fields, where is the weakest part of the magnetic field?
The bottom.
Can you see where the weakest part is?
Oh, it's
The top, isn't it? If you notice at the top, see here, if you wanted to try to avoid the magnetic field and you went this way, would you avoid it? No, you'd crash right into the magnetic field, wouldn't you? So here, let me back up a little bit. If I came this way, could I avoid the magnetic field by coming this way? Or would I crash right into it? I'd crash right into it. What if I came in from the top, like this? Could I avoid some of the magnetic field?
Yes.
Yeah.
I could. That would be the easiest way to get by the magnetic field. And in fact, it is the weakest part of the magnetic field, and so is the bottom part. They are the weakest part of the magnetic field, which is why, if you have ever lived in the north, Alaska people are very familiar with this, and people that live in South America are very familiar with this. During certain times of the year, you can look up in the sky and you see something called the Northern Lights. How many of you guys have ever heard of that? The Aurora Borealis, the Northern Lights. And you go, what is that? Okay, what it actually is the sun's particles going past the Earth, but what's happening is because the magnetic field is so weak, they're actually kind of going, because normally what happens is the sun has radiation that's poisonous. It would kill humanity. The only reason we survive on this planet is because our magnetic field pushes that radiation away. Okay? And so these particles that leave the sun, they come this way, and they hit our magnetic field from something called the solar wind. And our magnetic field actually pushes those particles around. Pushes those particles around the Earth, and it keeps us safe. Okay? But because the magnetic field is weakest at the top, some of those particles start to kind of come into our atmosphere, and you actually see them bouncing off of the atmosphere, and you can actually, they create light when you see that. And so it's a really cool effect, and I'll let you guys watch a video of that pretty soon, and you'll actually see, and when you sit there and you go, that's pretty cool, but if you really think about it, what that actually is sun particles bouncing off of the magnetic field. And I'll let you kind of take a look at that. Jason?
But isn't the Earth supposed to, like, around it, isn't the Earth supposed to, like, suck everything in, because the...
Now this is a magnetic field, right? Is a magnetic field the same as gravity?
No.
No, right? A magnetic field is not the same as gravity. A magnetic field is something completely different from gravity. So what you're looking at here is the magnetic field. That's something, this is how the Earth acts as a magnet. It has nothing to do with gravity. Okay? Yes?
My dad told me if you take a screwdriver and you bang it on the ground really hard, the molecules inside of the metal part will change and it will turn into a magnet.
He's very close, but he's got it backwards. We're gonna investigate that today, and you're gonna see. And next time you see Dad, say, Dad, you were sort of right. It does. I can do something with magnetism and a screwdriver, but it's backwards. And you'll see. We'll actually experiment that today. Okay, so what we're going to do today is we're going to take some magnets. But we're not going to look at how they interact with other magnets. What we want to do is we want to see how magnets interact with iron materials. Okay, so we know that they attract iron materials. The question is, do they do anything other than just attract? Do they do anything other than this? Okay, we know that magnets are weird around each other. The question is, does a magnet do anything to an iron piece of material, or does it just attract it? So we're going to investigate. We're going to play around with them, and we're going to do different things. And so what you're going to need right now is you're going to need a magnet that looks like this, and you're also going to need a bag of test objects. So very similar to what you did last time, except this time you're not going to be looking at whether the stuff sticks to the magnet. You're going to look and say, okay, well, the stuff that does stick to the magnet, does anything weird happen to that stuff? And so you're going to have to start really thinking about kind of how that works. So the very first thing that I want you to look at is the following. So let's come back to our notebook here. Let's go to our table of contents. We're going to come down. Okay, we've looked at how magnets interact. Today we're going to study something called the magnetic field. And that's what we just drew. It's that invisible field. I mean, you could almost even call it a force field. For those of you that are into Star Wars and stuff, it's like this invisible field that's around magnets. It's really odd. You can't see it, but you know it's there. You know it's there. Okay? Now, so let's take this magnetic field. I'm going to go to the next blank page of my notebook, and I'm going to add it there. Okay, and the first question that I want to ask, it's not my focus question, but it's just a thought, okay? So it's just a question. Something to just kind of look at, okay? And that's this. Let me make sure I word it right. And we sort of have investigated this a little bit because some of you kind of already found this. But the question is, can magnetism travel through materials? Or we could say, can magnetism not necessarily travel, but can it still work? Can it still do things? Okay? So can it travel or can it work through materials? Okay? So in other words, if I take a couple of magnets and I put stuff in between those two magnets, will the magnets still do what they do? Or will stuff stop them? Okay? It's an interesting question. So,
Well, it depends how strong they are.
oh, it depends on how strong, Jason says, depends on how strong the magnets are. Okay? But it could depend on a lot of things, and that's why we're going to be looking at this. So, for right now, what I want you to do is I want you to take a few minutes, maybe about 5 to 10 minutes, and take the magnets that you're going to receive, take your bag of test objects, and start putting stuff in between your magnets. Okay? So you might have, if you come back to your bag of test objects, you might say, okay, well, here are the materials I have. I'm going to take, I don't know, let's take this popsicle stick. Will this popsicle stick stop magnets from interacting with each other? Okay, so I might say, I'm going to put the popsicle stick between magnets, and I'm holding them right now. If I were to let them go, will they still stick?
Yeah.
Or will they fall because the popsicle stick stopped the magnetism? That's the question. Okay, so you're going to try all these different materials that are in here and see which objects stop the magnetism, or does it not make a difference? You'd say the magnetism goes right through them. Okay, so I'm going to have getter ones from my classroom go on up and grab, listen up, grab enough magnets for the people in your group and a bag of test objects and start investigating. Anything interesting that you discover, put it on today's meet, and make sure you're checking today's meet to see if people have questions or if you could want to respond to anything that someone might have said. Okay? All right, so we're going to take about 5 to 10 minutes to do this. We'll come back in a few minutes. ladies and gentlemen, you have less than 2 minutes to find out whether items stick or whether items block the magnetism. Okay, you're down to less than 15 seconds. you're down to 2 minutes.
You have to start
2 minutes. All right, ladies and gentlemen, time's up. Hands on your heads. 5, 4, 3, 2, and 1. So let's go ahead and get all our materials at the center of the table so we're not being distracted. So, did the magnet attract the steel paper clip through all materials? Did anyone find any materials that didn't work? Logan?
Straw.
Didn't work through the straw? Did you guys get it to work through the straw? Okay, it kept on moving, but if I flatten the straw, would it work through the straw?
Yeah.
Okay, so the straw works. Anything else? Jason?
The chip or whatever.
Okay, didn't work through the chip? Or how many of you got it to work through the chip? Okay, got lots of groups that got it to work through the chip. So what we found is we got it to work through pretty much all the materials that we had available. Okay? Now, was there anything interesting that you found as you were doing this? Why does it work? Is the question, right? Why does this work? So, I can come into my notebook here and just kind of take some notes to kind of model for you kind of what you should have been doing. Okay? And so as you're doing this, yeah, granted you're finding a lot of things, but you should also be writing stuff in your notebook. Okay? So, I might write something like, okay, magnets work through many materials. Might even draw a picture, okay, of a magnet here. Okay, and then maybe another magnet down here. And then label it, stick. And then magnets. So that I can come back later and understand what I was doing. Okay, because if you don't take notes, you're going to come back to this investigation 2 weeks from now, and I'm going to say, what was this investigation about? You're going to be like, I don't remember. Why don't you remember? Because I don't have any notes. Okay. So add some notes. Okay, the paper that I gave you, you're going to want to stick into your notebook. We're not going to do that just yet, but I'll give you an opportunity to do that. Okay? So the question is, why does this happen? So we're now going to put in our focus question. Okay? So here's your focus question. Make sure that you include it. And here it is. What happens to a piece of iron? comes close to or touches a permanent magnet. What happens to a piece of iron when it comes close to or touches a permanent magnet? Okay, that's the question, because we know that iron sticks to magnets. So, something must happen, right? Otherwise it wouldn't stick. When I look at a piece of iron and a piece of copper, does the iron act differently than the copper? Yes. The iron sticks to the magnet, the copper does not. So, would you agree that something odd is happening to the iron? Something must be happening to the iron that makes it want to stick to the magnet. So that's our question. What happens to a piece of iron when it comes close to or touches a permanent magnet? So we're going to investigate that. We're going to look at that a little bit closer. So finish writing this in your notebook. If you have finished writing this in your notebook, you might possibly want to grab a glue stick and take the opportunity to get this How Magnets Work sheet into your science notebook as well. What's that?
What's a permanent magnet?
Okay, I've got a question. What is a permanent magnet? Can anyone answer that? Logan, what is a permanent magnet? A magnet that never stops being a magnet, right? Okay, a bar magnet, or the magnets that you're using right now, those are permanent magnets. It will always be a magnet. Okay, come back 3 weeks from now, it's still a magnet. It's not going to stop being a magnet. Okay, it is permanently a magnet.
Well, I thought magnets are already permanent magnets.
Okay, so you've got a question. So I've got a question that says, I thought magnets were always permanent magnets. And we said, that's interesting that we would call some things permanent magnets, because if there are permanent magnets, that must mean there are also unpermanent is not a word.
Temporary.
There must be temporary magnets. Magnets that are only magnets for a little while. So what's the difference between a temporary and a permanent? A permanent magnet is always a magnet. A temporary magnet is only a magnet for a little while. And then it stops being a magnet. You go, what? That's weird. But that's what we're going to be looking at. Okay? So, once you have the stuff glued into your notebook, those questions glued into your notebook, what I'm going to have you do is take your materials. Find the objects that are iron. Okay? Because we're looking at an iron question. Find the objects that are iron and have them touch a magnet and see if anything interesting happens with the iron object that is touching the magnet. Okay? So you're going to have to experiment. You've got a bunch of stuff. I'm going to come around and give you some additional materials to kind of help you experiment. But let's take just a few minutes, not a whole lot of time, to take a metal object, an iron object, attach it to your magnet, and then see if you notice anything interesting about the iron objects once they are touching or they're close to a permanent magnet. Okay? So, let's go ahead and take a look at that right now, and we'll come back in just a few minutes and look at this part. So let's take 4 minutes.
Okay, so I don't have these.
Let's take 4 minutes to do that.
Alright? Okay, so
Yes.
how is this investigation supposed to happen?
Did you build a metal detector?
Banging a squirrel.
Be patient. There's some other things that you guys can play with. Okay. Here's some more things. And for the purposes of this, you might want to add some staples to their table so that it makes it easier for them to investigate.
Where's my magnet? object, and then it goes out of the object, and then it connects to the other object.
Okay. There's some more objects you can use. Investigate what happens to the iron when it's touching the magnet. Now we know it'll stick to the magnet. That's not what I want to know. I want to know, does anything weird happen to the iron when it's touching the magnet? Did you guys get staples here? Work together. Okay, I don't want to know that they stick. I know they stick. The question is, does anything weird happen to the iron when it's stuck to a magnet? Do this, what happens? So let's try and use another okay. So you're saying there's magnetism in the nail now? So if that was true, then what should this nail be able to do now? Which is interesting. Which means that this magnet is turning this nail into a... Right, because the only way this can happen would be if the nail is a... Alright, 10 seconds, ladies and gentlemen. Just don't dance, right? Alright, ladies and gentlemen, time is up. So, material, center of your table. In 5, 4, 3, 2, and 1. Alright. So, can anyone share with us what you discovered? Give me 1 second. Mr. Pearl's room. Yeah. Anything that is attracted to a magnet has iron in it. So the steel, anything that will stick has iron in it. That's what makes it magnetic. Yes, that's what we're going to talk about right now. Okay? Alright, okay, bye. Alright, so not only did you discover some pretty cool stuff, Mrs. Richards' class discovered some pretty cool stuff. So cool, in fact, that they had to call us and be like, what the heck is going on here? Okay, so we're going to talk about this. Okay? So let's just share out really quick. Serenity, what happened when you were doing this?
Well, what happened was the magnet, its magnetism traveled through the object, and now that object had now that object turned into a magnet, so it picked up other objects as well.
Okay, so that's pretty cool. Okay, we know that a magnet pick stuff up. Okay, but we also know that by experimenting, that if I were to take an object like, and let me put it here so we can see. If I were to take a washer, I know the magnet will stick to the washer. That's pretty obvious. Okay, but I've also got some paper clips here. The cool thing was that if I take this paper clip and I touch some things, the paper clip is picking up stuff. And you say, wait a minute, how is that possible? It's not the magnet that's doing it, it's the paper clip it's the washer that's picking up these paper clips. And you say, so wait a minute, so that means that in order for the washer to pick iron objects up, that means the washer must be it's got to be a magnet. How else can it stick? Now, here's the really interesting thing. If I were to take this magnet off and bring it back, okay, it falls off. But if I were to take another object, can I borrow your nail? If I were to take a nail and attach the magnet to it and come in and pick up some paper clips, not some paper clips, some staples, okay, like this, and hopefully you can see them, they're right there on the tip. Here's the interesting thing. If I remove the magnet, let me pull it out, it's still picking up paper clips. And you say, wait a minute, the nail is not a magnet. But right now, it actually is. Okay? Right now, it actually is. In fact, I might even be able to do it with the paper clip. That's heavier. Okay? If I were to take this nail, I can pick up a paper clip with it.
Awesome.
And you say, how's that possible? The nail is not a magnet. Okay? But what we're going to talk about right now is something really, really interesting. Okay? What you are observing, and we're going to get this into our notebook. Okay? What you're discovering right now is a concept known as induced magnetism. And what is induced magnetism? Okay, we would say that magnets induce. Okay, and we have to know what the word induce means. What does induce mean? Okay, and one of the things that I can think of, I know that when my wife was pregnant and she was going to have my daughter, one of the things they said is that, do you want us to induce? In other words, make you have her right now. Okay, so what does it mean to induce? It means to make something happen, right? So when we say magnets induce, it means that magnets, we could say they cause. So that's another word for induce. Okay? So magnets induce magnetism in iron objects. And that is awesome. And you go, well, what do you mean exactly by that, Mr. Brilla? Well, here's the thing. Okay? If I have a magnet, let's say I have a bar magnet, and this is the north pole, and this is the south pole of that magnet, right? And I have a nail. And here I'm going to draw a nail in a different color. And I've got this nail right over here that looks kind of like this. And it's got a pointy little tip on it. And normally the nail's not magnetic, right? Is it? No. But if you remember, we had a conversation about electrons and how electrons move, and that's what allows electricity to move, right? Electrons are negative, okay? And when there are no electrons, we would call that positive. Okay? Well, one of the things that makes metals really good at conducting electricity is that the electrons can move around. Okay? Now, it doesn't always work for all metals, but for objects that have iron objects have electrons that are easily moved by magnets. So, what happens is when you have a magnet that comes close to a nail, like this, what ends up happening is that electrons start to move. They start to move in one direction. So that one part of the magnet becomes, or that one part of the nail, so basically what this means is this part of the nail starts to become north, this part of the nail starts to become south. Because what's happening is all the molecules inside, all the atoms inside the nail are kind of moving around. And that would be like, let's say we had a classroom where boys and girls didn't get along. And the girls were sitting by the front of the class and the boys were sitting by the back of the class, right? And this new girl walks in and all the boys go, oh, it's a girl! And they all run to the front of the class. And all the girls that are in the front of the class, they go, oh, it's a boy! And they all run to the back of the class. And so now everyone has moved and shifted the whole class because this girl walked in. Same thing happens in the nail. When a magnet comes close to it, they start to shift. Okay? In iron, if the south pole is coming close to the nail, that part that's close to the nail starts to become a north pole. And the farthest part starts to become the south pole, and vice versa. So now, since this nail, so we would call this this is a permanent magnet, right? This was not a magnet, but it has now become one. We would call this a temporary magnet. Okay? So, what do magnets do when they're next to each other? Let's talk about what happens when two magnets come close to each other, one's north, one's south. They attract. Now, take a look at this nail. This nail, when it came close to the magnet, has become a magnet. So what's going to happen when the nail comes close to the magnet? They're going to attract. They're going to attract and they're going to stick. Is that true?
Yes.
Is this nail going to stick to the magnet?
Yes.
Yes. Okay, and so what we're actually starting to discover is we're starting to discover how exactly an object sticks to a magnet. Because when I take a washer, okay, so let me come back and I'm going to put it here in the desk cam. Okay, when I take a washer and when I take a washer like this, is this washer a magnet? No, it doesn't do anything. I know it's not a magnet because it doesn't do anything here. It doesn't lift anything. Okay? It's not a magnet. It doesn't do anything. Okay? However, when I bring this washer close to a magnet, okay, the field lines of this magnet, right here, the magnetic field of this magnet is starting to do something to the atoms of the washer. And the atoms of the washer are starting to move around and line themselves up the same way that we said if a girl walked in through that door. The atoms of the washer are starting to move around so that the washer is starting to become a magnet. And once the washer becomes a magnet, now I have two magnets next to each other. What's going to happen? They're going to stick. Like this. So they're stuck. Why? Because I have two magnets right now. One is the washer. One is the magnet. Okay? One of them is a permanent magnet. The other one is a temporary magnet. And the question is, well, how did that washer become a magnet? Well, that washer became a magnet because magnetism was what? What's the word that I'm looking for? That washer became a magnet because magnetism was induced in the washer. Okay, the washer was induced to become a magnet. That is a key word because anytime you have a metal object, an iron object, when it becomes a magnet or sticks to an object that is a magnet, you have to call it induced magnetism. How does an iron object become a magnet? Aubrey, you're done with science. How does an iron object become a magnet? It becomes a magnet through induced magnetism. Okay, now, what does that mean? So let's come back, because I know that someone in my class said earlier, well, my dad told me that if you bang a screwdriver on the ground really hard, it becomes a magnet. And I said, you're close, but not quite 100% right. Okay, does banging a magnet make a difference? Can I bang, let's see, let me switch here. Okay, can I bang an object and turn it into a magnet? Okay, if I have a nail that is not a magnet, do you think banging it around is going to make the atoms line up the way they should?
No.
What do you think? You think so? Or do you think if I bang them around, they're just going to go all over the place?
All over the place.
They're going to go all over the place. There's nothing that makes them want to be lined up in a certain way. Okay? And that's like me saying, if I take a puzzle and I throw it up in the air, it's going to land and it's going to make itself. Is that going to happen?
No.
It'll never happen. I can take a puzzle and throw it up. They'll never land in a position where they make itself. Okay? Something has to make itself, right? In order for that to happen. So when you're talking about magnetism, I can take a nail and I can turn it into a magnet. Okay? I can take a nail like this. That's not a magnet, and I can prove to you it's not a magnet because I can come here and say, okay, I'm going to pick stuff up with it. And it doesn't pick anything up. Okay? So you'll see, this nail, is it a magnet?
No.
Is it behaving as a magnet?
No.
No, it's not. It's not doing anything. So I can prove this nail is not a magnet because it's not doing anything. Now, if I take this nail and I put a magnet on it, what am I doing to the nail?
You're putting
I am doing what to it? I am inducing magnetism in it, which means that when I rub this magnet on the nail, what's happening to the atoms inside the nail? They're moving around and they're lining up in a magnetic type position. So when I remove this magnet, this nail, the atoms in it are lined up, right? So if the atoms are lined up, what should happen to this nail?
it should stick.
It should still be a magnet. If I come down here, you'll discover that that's true. I can pick up paper clips with it. So that doesn't happen by me banging it around on the floor. That happens by me doing what?
Rubbing a magnet.
Rubbing a magnet on it. I'm lining them up. Now, here's the thing. Watch, it's a magnet, right? I can take them off, put it back down, and do it again. It's going to stay a magnet. It's going to stay a magnet. And in fact, if you have a really strong magnet, which I have some here in my classroom, okay, if you have a really strong magnet, what is known as a rare earth magnet, something that looks like this, and you rub that on the nail, okay, because the magnetism of this magnet is a lot stronger, do you think it's going to induce stronger magnetism in the nail?
Yes.
Yes, the nail is going to become a lot more magnetic because of that. I can come down here and you'll see that I can pick up a whole lot more stuff with it. Okay, here it wants to pick up the paper clip, but it's picking up quite a few of the paper clips. Okay, so staples. Okay, if I had a smaller paper clip, it would probably pick it up. And there it is. See, you notice it is picking it up somewhat. If I go slow, it should pick it up. There it is. So this nail is a magnet. Its atoms are lined up just like a magnet. Now, how do you think I could take these atoms in this nail and put them back to their original position?
Bang them on. Bang them.
Bang it around. Okay? If I were to take it and just bang it on the table, you think this is causing the atoms to move around?
Yes.
Now, is it causing them to move around and line up like a magnet, or causing them to go all over the place?
Go all over.
There's now going back all over the place, which means by banging it, I didn't give it magnetism, I took it away. Now, if I come back here and I try it again, you will notice it will no longer pick anything up.
That's how it was
Okay,
backwards.
so it's the opposite. Banging a screwdriver that you put a magnet on the floor is going to take away its magnetism. Okay, rubbing a magnet on it is going to give it magnetism. And in fact, this is something that, if you understand it, is extremely useful. Okay, I've taken this idea before when I'm working on a car or working on something and I drop a screw that I can't reach. I just take a screwdriver, or I take a long metal object and I do this to it. And then I reach in with the little metal object and I can very easily pick up whatever it was that I dropped. Okay, so induced magnetism is a really cool concept. and it's important for you to put it into your notebook to make sure that you understand it. Let's come back to our notebook. Okay. The other thing that I want you to make sure that you understand is that when you induce magnetism, the object that is being induced becomes a magnet. So let me write this in here to make sure that you don't have it. Okay? So I'm going to say induced magnetism creates what kinds of magnets? Temporary magnets. So earlier I had someone say, well, aren't all magnets permanent? Well, we have the answer now. Are they?
No.
Okay. Induced magnetism creates temporary magnets. Magnets that are only magnets for a little while because their atoms are aligned up correctly. But at some point, if you realign all those molecules in a format that is not north-south, it is no longer going to be a magnet. Okay? And so that's how all magnetic objects will stick. So when you think of your chair and you stick your magnet to your chair, what's happening to the leg of your chair that's making it stick to the magnet? The chair is lining up so that it wants to stick to the magnet. The molecules in the leg of the chair are kind of aligning themselves to create a temporary magnet out of the bottom leg of the chair so that the object will stick. So anything that attracts and sticks to a magnet is having magnetism induced in it, and that's why it's causing it to stick. Aubrey, question?
No, it's not a question, but I told my dad that I think that it probably could be handy for some things, and then he told me that it's actually very handy, like if I'm up high and I'm taking screws out of a light pole, and I don't want to drop them, it will just stick to the metal.
Absolutely. It's very useful. Induced magnetism is very useful, especially if you're putting screws into a wall. If you're up and you're putting a screw on the screwdriver, could you induce magnetism in the screwdriver to have it hold the screw for you?
Yes.
Yeah, that'd be a smart thing to do. You would induce the magnetism in the screwdriver. Then you would stick the nail to the tip of the screwdriver, or the screw to the tip of the screwdriver. Would the screw stay?
Yeah.
It should. And therefore, what does that mean? That means you don't have to hold the screw and then try to screw it in at the same time. Okay, you could actually focus on just doing what you need to do and not have to worry about holding the screw on the screwdriver. Okay, now, we know that a magnet has a magnetic field. We've talked about that. Sophia, can you find the spring for me? We know that a magnet will induce magnetism in an iron object. Okay, does it have to touch the object to induce magnetism? What do you think, Hakeem? Does a magnet have to touch something to start to turn it to a magnet? Or do you think that the object could start to become a magnet even though it's not being touched? Has to be touched. Okay? Alright, so what I'm going to do right now is I'm going to work on a little experiment that I want to show you. I did this in my classroom last week. Okay? But what I have here is I have a bottle with a very strong magnet right here. And I'm going to take a piece of string and I'm going to tape it to the table here.
Oh, that.
Okay? And what we're going to see is, I'm going to take a look and see if I can induce magnetism in an object without having to touch it. Now, how do I get this, how can I get this paper clip to want to stay stuck to the magnet? What would have to happen to the paper clip to have it stick to the magnet?
It would have to fly. It would have to pull.
So the only way that this paper clip can stick to the magnet is for the paper clip to become what? A magnet. And you'd say, well, you'd have to make it touch. Well, what I'm going to do now is I'm going to try to induce that magnetism in this paper clip without actually touching it. Okay, so
It was easier last week, I bet, with the other magnet. We did it!
okay, so if you take a look, and I'll bring this down here. Okay, the paper clip has not touched the magnet yet. But yet, if you really take a look, you will notice the paper clip is doing what? Okay? The paper clip is floating in the air. Okay, and I'll see if I can focus in here so you can see it. Okay, I'll touch the string here. So you can actually see the paper clip is floating in the air. So what's causing that paper clip to stay there? Well, the paper clip, is it wanting to stick to the magnet?
Yeah.
It is, which means that paper clip must be a magnet. How can it be a magnet? I haven't touched the magnet yet. So does an object have to touch the magnet for induced magnetism to take place?
No.
No. Okay, and that's what we were talking about earlier when we were drawing those field lines. Okay, a magnet has a magnetic field that comes out of the magnet. As soon as an iron object starts to enter that magnetic field, what do you think starts to happen to that object?
It starts to induce.
Okay, as soon as an iron object enters the magnetic field, magnetism starts to be induced. Okay, so what you're looking at here is this paper clip has induced magnetism in it that makes it want to stick to the magnet. Okay? It makes it want to stick to the magnet, even though it's not a magnet. And because the string is keeping it from going anywhere, it's floating in the air. Okay? It's a really weird concept. It's really creepy to look at. It works with these magnets because they're really strong. But you could make it happen with any magnet as long as you had them strong enough to pull the object and keep it up in the air. Okay, so I'm going to leave this here for now so you guys can continue to kind of look at it. But let's go back to our notebook for a little bit. And then add one more note.
Okay.
Okay, and the last note that we're going to add here is we could say that magnets do not need to touch iron objects to induce. Okay, that's important. And so I'll draw a picture of a magnet. So let me draw one of these magnets that we're using. Okay. So this is the north side, this is the south side of the magnet. And what I have is I have field lines that go like this. Okay, and I'm going to call these field lines. What kinds of field lines? They're magnetic field lines. Can you see them?
No.
You can't. Now, there's a cool way for you to actually be able to see what they look like,
Wow.
but I'm not going to share with you just yet.
No.
But there's a really cool experiment where you could take a magnet and then put some stuff on it, and you'll actually be able to see the field lines. It's pretty awesome. Okay, so the magnetic field lines look like this. Okay, and I'm going to write here, entering the magnetic field induces magnetism. Now, why is the magnetism stronger if you touch the magnet than if you're on the outskirts of the magnet? Where are the magnetic fields the strongest? Far from the magnet or close to the magnet? Close to the magnet. So the closer you get to the magnet, the stronger the field lines. And if you touch it, then yeah, you're getting the strongest magnetic field, and that's going to induce more magnetism. That's why if you touch the magnet to the metal object, that's going to give you the strongest temporary magnet possible. But if you just get close, that's going to induce some magnetism. Okay, evidenced by coming back and looking at this picture where I see the paper clip floating. Okay, some magnetism has been induced in that paper clip, and I can see it because it's attracted to the magnet. Okay, but it's probably not as strong as if I actually touched it to the magnet. Okay? Does that make sense? Jason, question.
Wait, so if you're saying if you get close to the magnet, then there will already, there will, the little the magnets inside the metal, it will start lining up if you get close to the magnet.
As soon as you enter that magnetic field,
Oh, okay. And if you connect a nail to the north and south, and the nail becomes a north and south, well, if you try to put it to a magnet and it's on the wrong side, will it push it away because it's a magnet?
that's okay. So yeah, so Jason asked a really interesting question. He said, if I turn a nail into a magnet, and then I flip it around and try to touch it, is it going to repel the magnet? What do you think? Can I get a nail to repel a magnet, or will it always stick to a magnet? That's an interesting question. So let's do that. Grab your nail, stick it to your magnet, and then flip the nail around and stick it to the magnet. See if it sticks again or if it repels. Okay, so take about 10 seconds to do that. Stick it to one side, then flip it around and stick it to the other side, and see if it still sticks.
So this side sticks.
Okay? Alright, 5, 4, 3, 2, 1. Does it still stick? It still sticks. So, you say, wait a minute, I thought they're supposed to repel. So what happens if I bring the nail close to the south? The part closest to the nail becomes a north. Now if I flip the nail around, and the other side was the south, and now I bring it close to the north, what's going to happen? Because the atoms in the molecule, because the molecules in the nail can realign themselves really quickly, okay, the part that I bring close to the magnet will always make itself opposite of whatever it's closest to. Does that make sense? So if I have the north side of a magnet and I bring a nail, that part of the nail is going to become south so that it can stick. If I flip the nail, it's going to realign itself to make that part south. So whatever object I use, whatever metal object I use, when I bring it close to a magnet, it's always going to align itself to be opposite of the side that you're bringing it close to. So you can never get two metal objects to repel each other because they're always going to align themselves so that they're opposite of what the magnet is so that it will stick. Aubrey?
On Friday, you said something about like if you get, I forget what type of scan it is, but if you go through and you have metal, it will yank it from you. So if you have no metal on you, but you go through it, does it kind of make you metal because you're going through it?
Well, are you made of iron?
No.
So an MRI machine would not induce magnetism in you because you're not
Iron.
You're not made of iron. Okay, but you do have ions in your body, and so what happens is that magnetism in a weird sort of a way does sort of induce magnetism in your atoms, and the cells in your body kind of align themselves, and they can read that information, and that's what they use to take pictures. So it's pretty cool technology, way more advanced than what we can talk about here, but it works along the same basic concept. Okay. All right, so that's induced magnetism. If you look at the questions you had on your paper, there were two other questions, and I'm going to put it down here at the bottom. Okay. What was the second question?
What happened to a piece of iron?
What's the second question?
How can a magnet make a paperclip float in the air?
How can a magnet make a paperclip float in the air? You've seen it, right?
Yeah.
You say, well, the magnet makes the paperclip become a temporary magnet. Therefore, the paperclip wants to stick, but if you put a string on it that doesn't allow it to stick, the paperclip will just float. Okay? And number 3, what happens to a steel nail when a magnet touches it? Okay, so hopefully now you can tell me what's actually happening inside the nail that's making it become magnetic. Okay, can anyone describe it in their own words? Like what's happening inside the nail, Logan?
Molecules inside are running around.
Yeah, they're moving around and aligning themselves to do what?
To turn themselves into a magnet.
Yeah, they're aligning themselves magnetically just like a magnet, and therefore the nail becomes magnetic. and they will stay magnetic until either time goes by and they kind of realign themselves slowly over time, or unless you
Bang it really hard.
bang it or shake it into something and force those molecules to move around again, and that'll get rid of the magnetism that you induce in that object. Okay, so pretty interesting, pretty cool concept. Any other questions before we move on? Vincent.
When we were just seeing if the magnets can work out, like the nails can work out, I think that if I tried to put the nail a certain way next to the side of the magnet, they wouldn't go.
Okay. You probably didn't get it to go because the nail will always realign itself no matter where it is. Okay, Ramson.
Okay, so this is a question. When you said about the sun radiation, I automatically did this. If the Earth's magnet field is so strong, it can push most of the sun's radiation, then how come normal radiation still damage your body and it's not as strong as the sun radiation? Because that, I don't know.
Okay, why does radiation affect your body? Is that what you're saying?
No, what I'm saying is how come normal radiation can still damage your body?
What is normal radiation?
Normal radiation is just any kind of radiation.
Yeah, any kind of radiation will damage the body. And the sun blocks most of it. Okay?
Yeah.
But one of the things we've discovered is through pollution, we've affected some of the stuff that's in our atmosphere, like ozone. Ozone blocks radiation as well. It blocks certain types of radiation. And because pollution that we put into the air, some of that ozone in the atmosphere is being kind of going away, and so more radiation is getting through, and that's why we now need to use sunblock and stuff to block some of that radiation, because it does cause problems to the skin. Okay, but we'll come back to it later because that doesn't have a whole lot to do with magnetism. Okay? All right. So with that, we're going to leave it at that. You had a question. What was your focus question for this investigation?
What happens to a piece of iron when it comes close to or touches a permanent magnet?
So what happens to a piece of iron when it comes close to or touches a permanent magnet? That was your focus question. Let me come back to it, because you always have to come back to what you were looking at the beginning. And here's my question. Can you answer that question? Can you answer what happens to a piece of iron when it comes close to a magnet or touches a permanent magnet? You think you can?
Yeah.
Okay. You'd want to answer it using academic vocabulary, using the words that we've learned in science, and prove to me that you understand. Okay. Don't just say, it makes them become magnets. Anybody can say that. The question is, do you understand what's actually happening? Okay. So, during our writing block or during anybody's writing block in the other classrooms, take some time to answer this question, and that's going to do it. So we're going to go ahead and sign out from our classroom. Thanks so much for joining us, and we will see you soon.
Still